The end of the Cold War produced a brief and dangerous illusion that technological superiority had reached a terminal state. By the mid-1990s, air power doctrine in the United States rested on a quiet but profound assumption that the combination of low-observable shaping, radar-absorbent materials, and predictable enemy air defense behavior had rendered a certain class of aircraft effectively untouchable. The F-117 Nighthawk was not merely a combat platform. It was a physical manifestation of that assumption. Every facet of its design reflected a singular philosophy: survival through invisibility rather than speed, maneuverability, or structural redundancy. The aircraft's geometry was a study in deliberate compromise. Its faceted surfaces were not aesthetic choices, but mathematical necessities, derived from early computational limits in radar cross-section modeling. Each flat panel was oriented to scatter incident radar energy away from the emitter, minimizing coherent return. This approach imposed severe aerodynamic penalties. The airframe was inherently unstable in all three axes, demanding a quadruple redundant fly-by-wire system to maintain controlled flight. Structural integrity, therefore, depended not only on material strength, but on uninterrupted electronic mediation between pilot input and control surface response. Beneath the angular skin lay a conventional aluminum-lithium alloy structure, selected not for stealth, but for weight efficiency and manufacturability. Unlike later stealth aircraft that integrated composites as load-bearing elements, the F-117 relied on traditional spars, ribs, and frames to carry aerodynamic loading. These components were never designed to endure high-G maneuvering or sustained turbulence. The aircraft's operational envelope was narrow by design, optimized for smooth, predictable flight profiles at night, at altitude, and along pre-planned corridors. Structural fatigue cycles were calculated under the assumption that the jet would rarely experience abrupt aerodynamic stress or evasive maneuvers. The true innovation and vulnerability lay in the outer layers. Radar-absorbent material coated nearly every external surface, applied in multiple strata with precise thickness tolerances. These coatings converted electromagnetic energy into heat, dissipating radar returns before they could re-radiate. However, RAM was not structurally inert. It aged, cracked, and delaminated under thermal cycling, moisture ingress, and mechanical vibration. Each flight imposed microscopic degradation, particularly along panel seams, access doors, and leading edges where aerodynamic loading was highest. Maintenance crews compensated through constant inspection and reapplication, but the process was as much art as science. Stealth, in practice, was never absolute. It was probabilistic, contingent on frequency bands, aspect angles, and environmental conditions. The F-117's design optimized survivability against high-frequency fire control radars, not the lower-frequency search radars developed decades earlier. Those legacy systems, dismissed as obsolete, lacked precision but possessed wavelength characteristics that interacted differently with faceted surfaces. Their returns were weak, fleeting, and noisy, but not non-existent. The assumption was that such signals were tactically irrelevant, unable to guide weapons with sufficient accuracy. This assumption would prove fragile. By 1999, during NATO's air campaign over Serbia, the F-117 was no longer a secret weapon but a known quantity. Its flight profiles had become predictable. To minimize exposure, mission planners reused ingress and egress routes, trusting stealth to compensate for repetition. Each sortie followed nearly identical timelines, altitudes, and headings. This operational regularity simplified logistics and reduced pilot workload, but it also created patterns, statistical footprints in time and space that could be observed, analyzed, and exploited. On the night of March 27th, atmospheric conditions over central Serbia were unusually cooperative for ground-based radar operators. A temperature inversion trapped moisture near the surface, altering radar propagation characteristics. Low-frequency emissions traveled farther and with less attenuation than expected. Intermittent cloud layers introduced scattering effects that momentarily enhanced radar returns from objects otherwise difficult to detect. These were not dramatic anomalies, but subtle deviations, small enough to be dismissed in isolation, yet significant in combination. As the F-117 entered hostile airspace. It carried no radar warning receiver capable of interpreting emissions from antiquated systems. Its defensive suite was optimized for threats it was never meant to encounter. The aircraft flew clean and steady, maintaining strict adherence to its pre-planned route. At this point, aerodynamic loading on the airframe was minimal. Control inputs were small, and the fly-by-wire system compensated continuously for inherent instability, maintaining a delicate equilibrium between lift, drag, and control authority. On the ground, a surface-to-air missile battery operated equipment whose design lineage traced back to the 1950s. Its components were bulky, analog, and slow by modern standards. Yet these limitations conferred a different kind of resilience. The radar operated in a frequency band that interacted unpredictably with stealth geometries. Operators used short, intermittent bursts rather than continuous illumination, reducing the likelihood of detection and exploiting moments when radar cross-section spiked due to aspect angle or surface irregularities. At a specific point in its flight path, the F-117 presented a transient vulnerability. Minor yaw corrections exposed panel edges and internal cavities, engine inlets, exhaust apertures, and access seams, creating a brief increase in radar return. Simultaneously, accumulated wherein the radar-absorbent coating along a leading edge may have altered its electromagnetic properties. The degradation was microscopic, invisible to the naked eye, but sufficient to reduce absorption efficiency at certain wavelengths. Stealth, at that instant, degraded from improbability to possibility. The radar contact was fleeting, ambiguous, and easily dismissed. But it was enough. Using optical tracking and predictive targeting rather than continuous radar guidance, the missile battery prepared a launch solution. The weapon itself was a study in brute force rather than finesse. Its guidance system lacked the precision of modern seekers, but its warhead compensated through sheer explosive yield. It did not require a direct hit. Proximity was sufficient to induce catastrophic structural failure. When the missile detonated near the aircraft, the effects propagated faster than human perception. The blast wave imposed an instantaneous overpressure on the airframe, exceeding design limits in localized regions. Thin aluminum skins, already compromised by cutouts and faceted joints, experienced abrupt plastic deformation. Structural integrity failed not globally, but asymmetrically. A wing panel lost load-bearing continuity, redistributing aerodynamic forces unevenly across the remaining structure. This redistribution triggered a cascade. Control surfaces responded, but the fly-by-wire system was now compensating for damage it had never been programmed to interpret. Sensor inputs became inconsistent. Actuator commands reached surfaces no longer rigidly attached. Aerodynamic loading increased sharply as the aircraft departed controlled flight. Within seconds, stresses exceeded ultimate material strength in multiple components. Fracture propagation followed pre-existing fatigue paths, tearing through rivet lines and spar junctions. The aircraft disintegrated not in a single explosive moment, but through a rapid sequence of structural failures, each amplifying the next. Lift collapsed. The pilot ejected into darkness as the remaining airframe descended, its stealth skin irrelevant against gravity and inertia. The illusion of invulnerability ended not because the aircraft was poorly engineered, but because it was engineered for a world that no longer existed. In that night over Serbia, the decisive factor was not the missile's age or the aircraft's novelty, but the interaction between design assumptions and operational reality. Stealth had reduced risk, not eliminated it. Materials aged. Patterns formed. Physics remained indifferent to doctrine. The F-117 was never invisible. It was merely difficult to see until the conditions aligned and difficulty became insufficiency. The mission profile that night was unremarkable precisely because it was designed to be. The flight plan reflected a doctrine that prized consistency over improvisation. Predictability was treated not as a vulnerability, but as an efficiency multiplier. The F-117 Nighthawk departed under conditions considered optimal for low-observable operations, darkness, moderate altitude, and a stable atmospheric column that promised minimal turbulence. From an engineering standpoint, the aircraft was operating well within its certified limits. No component was being stressed beyond what designers had anticipated. And yet, the true stresses acting on the system that night were not those measured by strain gauges or flight data recorders. At cruise, the aircraft existed in a delicate aerodynamic equilibrium. Its faceted planform produced lift inefficiently, requiring higher angles of attack than conventional fighters. This imposed continuous corrective inputs from the flight control computers, translating into constant micro-adjustments at the control surfaces. Each correction generated small but cumulative loads on hinges, actuators, and attachment points. Over hundreds of sorties, these loads contributed to low amplitude, high cycle fatigue, exactly the type most difficult to detect during routine inspection. None of this represented imminent danger in isolation. Together, they formed a background condition of structural stress that defined the aircraft's true state at the moment it crossed into hostile airspace. Externally, the airframe interacted with an environment far more complex than mission planners acknowledged. Atmospheric stratification that evening created variable refractive layers, subtly bending radar energy near the surface. These layers did not enhance detection uniformly. Instead, they produced intermittent propagation anomalies. From a physics perspective, this meant that electromagnetic waves emitted from ground-based systems behaved inconsistently, occasionally returning signals stronger than predicted by standard models. Stealth design assumes statistical averaging, many weak returns canceling into irrelevance. On this night, averaging failed. The aircraft's outer skin bore the cumulative imprint of years of operational compromise. Radar-absorbent coatings, though meticulously maintained, were subject to erosion from rain, dust, and thermal cycling. Each application introduced minor variations in thickness and material composition. Over time, these variations produced non-uniform absorption characteristics across the airframe. At certain frequencies and at certain angles, these imperfections acted less like absorbers and more like scatterers. The stealth envelope narrowed imperceptibly, not through catastrophic failure, but through gradual material aging. As the aircraft approached its target area, its orientation relative to the ground-based threat environment became critical. Stealth geometry is highly aspect-dependent. Head-on, the aircraft presented minimal radar cross-section. Slight yaw or roll deviations, however, exposed edges and cavities never intended to face emitters. On this sortie, minor course corrections, routine, almost subconscious, altered the aircraft's aspect just enough to intersect a detection window. This was not pilot error. It was the inevitable result of flying an inherently unstable shape through a dynamic atmosphere. On the ground, operators of the S-125 Niva were not searching for a clear radar image. They were searching for anomalies, brief, inconsistent blips that defied background noise. Their system lacked the resolution to track stealth targets continuously, but it excelled at persistence. By emitting in short bursts and correlating returns over time, they exploited a weakness not in the aircraft, but in the assumptions surrounding it. The aircraft was not detected as a stable object, but as a recurring disturbance in the electromagnetic environment. The stress on the F-117 at this stage was not mechanical, but systemic. Its defensive systems were blind to the nature of the threat. Radar warning receivers were tuned for modern fire control radars, not legacy systems operating outside expected parameters. This mismatch created a false sense of security within the cockpit. The aircraft's systems reported normalcy because they were incapable of perceiving abnormality. Situational awareness, in this context, was constrained by design philosophy rather than human limitation. As the aircraft continued along its ingress route, it encountered subtle aerodynamic disturbances caused by localized wind shear. These disturbances imposed transient increases in aerodynamic loading on the wings and tail surfaces. Again, these loads were well below structural limits, but they demanded additional corrective action from the flight control system. Control surfaces deflected more aggressively, momentarily altering the aircraft's radar signature. The interaction between aerodynamic necessity and electromagnetic vulnerability was unmodeled, not because it was unknowable, but because it was deemed irrelevant. Internally, the aircraft structure absorbed these forces unevenly. Load paths shifted through spars and frames, concentrating stress at junctions already weakened by fatigue cycles. Riveted joints, particularly along panel edges, experienced microslippage. Adhesive bonds beneath the ram layers endured shear stresses they were never designed to carry repeatedly. None of this compromised flight safety in a traditional sense. It did, however, reduce the margin between nominal operation and structural failure should an external shock occur. That external shock arrived not as a direct hit, but as proximity. The missile's detonation produced a rapidly expanding pressure front, interacting with the aircraft's surfaces in milliseconds. But before that moment, the conditions enabling the engagement were already in place. Detection had occurred not because the aircraft failed, but because its design assumptions intersected with an adversary willing to exploit statistical improbability. The stress acting on the system was cumulative, layered, and largely invisible. In this phase of the event, the aircraft was still intact, still controllable, and still performing its mission. Yet its fate had already been determined by a convergence of factors extending far beyond the moment of impact. Structural integrity had been subtly compromised by fatigue and material aging. Aerodynamic stability depended entirely on uninterrupted electronic mediation. Stealth effectiveness rested on probabilistic margins eroded by environmental conditions and operational predictability. The aircraft was not overwhelmed by force, it was cornered by physics. Every system functioned as designed, but design itself proved insufficient when confronted with a threat outside its conceptual framework. The stress acting on the F-117 that night was not excessive, it was simply unaccounted for. And in engineering, what is unaccounted for is often what matters most. The stage was set long before the missile left its rail. By the time the engagement sequence began, the aircraft existed in a narrow corridor between survivability and vulnerability, sustained by assumptions that no longer held. The anatomy of stress in this event was not a single load or force, but an accumulation of small, rational decisions that collectively reduced resilience. What followed was not an accident in the traditional sense, but the inevitable resolution of a system operating at the edge of its design philosophy. The transition from survivability to failure occurred in a time window measured in milliseconds. There was no warning tone, no progressive escalation, no opportunity for human intervention. The S-125 Neva was never designed to surgically dismantle advanced aircraft. It was designed to impose overwhelming stress on targets assumed to be structurally conventional. Against the F-117 Nighthawk, this brute force philosophy interacted with an airframe optimized for an entirely different threat model. At the moment of missile proximity detonation, the aircraft was traveling at subsonic speed in stable, wings-level flight. Aerodynamic loading across the airframe was symmetrical. Lift distribution along the wing panels was uniform within expected tolerances, and control surface deflections were minimal. This state of equilibrium is critical to understanding what followed, because the failure did not originate from an overloaded maneuver or pilot-induced stress. It originated from an external impulse applied to a structure already operating near the lower bound of redundancy. The missile's proximity fuse initiated detonation at a calculated standoff distance, producing a rapidly expanding spherical shock wave. The pressure gradient imposed by this blast front rose faster than the airframe could elastically respond. In conventional aircraft, curved surfaces and continuous load paths help distribute such loads. The F-117's faceted geometry did the opposite. Flat panels presented normal surfaces to the shock front, concentrating impulse loads at panel boundaries and fastener lines. This created localized regions where stress exceeded yield strength almost instantaneously. The first mechanical failure occurred at the skin level. Aluminum alloy panels experienced abrupt plastic deformation, particularly along edges bonded and riveted to underlying frames. The presence of radar-absorbent material altered the failure mode. Ram layers, designed to absorb electromagnetic energy, offered no structural reinforcement. Under blast loading, they fractured and delaminate, stripping away from the substrate and exposing bare metal to further pressure differentials. This delamination removed any residual damping effect, allowing vibrational energy to couple directly into the airframe. As the shock wave wrapped around the fuselage, asymmetric loading developed. One wing experienced a higher impulse than the other due to relative orientation at the moment of detonation. This imbalance induced an immediate rolling moment. The flight control computers sensed the deviation and commanded corrective deflections, but the response lag was measured in tens of milliseconds, an eternity at the structural level. During this lag, load paths shifted violently. Spars designed for steady aerodynamic loads were suddenly subjected to combined bending and torsional stresses well outside their design envelope. The most critical failure occurred at a wing root junction. This region already carried high baseline stress due to the aircraft's inefficient lift distribution. Fatigue cycling over years of operation had introduced microcracks along fastener holes and adhesive interfaces. Under normal conditions, these defects were stable. Under blast-induced overpressure, they became fracture initiation sites. Crack propagation accelerated along rivet lines, severing load transfer between skin, ribs, and primary spar. Structural integrity was lost locally, but the consequences were global. With the wing's load-bearing continuity compromised, lift on that side collapsed. The aircraft entered an uncommanded roll coupled with a yaw excursion. Aerodynamic forces amplified the motion, increasing dynamic pressure on remaining intact surfaces. Control surfaces responded aggressively, but they were now acting on a structure whose stiffness characteristics had changed unpredictably. Actuators commanded deflections that imposed additional stress on already damaged attachment points. In several locations, hinges and control rods experienced overload and either jammed or detached. Internally, sensor data became incoherent. Accelerometers registered spikes beyond calibrated limits. Gyroscopic references diverged as rotational rates exceeded expected bounds. The flight control system, designed to stabilize an unstable but intact airframe, attempted to reconcile conflicting inputs. Its algorithms assumed structural continuity. They were never meant to manage partial disintegration. Control laws commanded corrections that, in practice, accelerated failure by driving aerodynamic loading into weakened regions. Within seconds, the aircraft transitioned from controlled flight to dynamic breakup. The fuselage experienced torsional twisting as differential lift and drag acted along its length. Frames designed to maintain shape under distributed loads buckled under concentrated stress. Skin panels peeled away, exposing internal systems to direct airflow. This exposure introduced new aerodynamic forces, further destabilizing the structure. The aircraft was no longer a coherent aerodynamic body, but a collection of failing components interacting chaotically with the airstream. The pilot's experience during this sequence was dominated by violent motion and system alarms that conveyed no actionable information. Ejection decision-making in such scenarios is constrained by physics rather than training. As structural breakup progressed, the probability of a survivable ejection window diminished rapidly. The ejection seat itself relied on predictable airflow and structural orientation to function as intended. Delay increased risk exponentially. When ejection occurred, it was not an escape from a single catastrophic moment, but from an unfolding structural collapse. The remaining airframe continued to fragment after pilot separation. Sections impacted the ground across a wide debris field, each bearing evidence of distinct failure modes. Some components exhibited ductile tearing, indicative of overload. Others showed brittle fracture patterns associated with high strain rate loading. The wreckage told a story not of instantaneous annihilation, but of sequential mechanical defeat. From a forensic perspective, the key insight is that no single component failure doomed the aircraft. The missile did not destroy the F-117 in the colloquial sense. It imposed a stress environment for which the aircraft had no tolerance margin. The design philosophy prioritized low observability over damage tolerance. Redundancy existed in electronics, not in structure. Once the airframe's primary load paths were disrupted, recovery was mechanically impossible. This moment of failure exposes the central paradox of stealth-era engineering. By minimizing radar cross-section, designers accepted geometries and materials that sacrifice structural resilience. Flat panels, sharp edges, and thin skins reduced electromagnetic signature but increased susceptibility to blast and fragment damage. The assumption was that stealth would prevent engagement entirely. When that assumption failed, there was no secondary layer of survivability to absorb the consequences. The missile that night did not defeat stealth through superior technology. It defeated it by introducing energy into the system faster than the system could adapt. Structural integrity failed because it was never meant to be tested under such conditions. Aerodynamic loading became destructive because it acted on a structure no longer continuous. Material failure propagated along paths laid down years earlier by fatigue and compromise. In engineering terms, the catastrophe was not a surprise. It was a boundary condition finally reached. The aircraft crossed from the safe side of probabilistic survivability into a regime where all assumptions collapsed simultaneously. At that boundary, control became irrelevant, and physics asserted absolute authority. The recovery of the wreckage began hours after impact, under conditions defined more by urgency than by methodological clarity. Unlike civilian accidents governed by standardized international protocols, the forensic environment surrounding the downed F-117 Nighthawk was fragmented, politically constrained, and operationally asymmetric. The debris field extended across multiple kilometers, a spatial signature consistent with in-flight structural breakup rather than ground impact disintegration. This dispersion pattern immediately ruled out hypotheses of controlled descent or delayed failure. The aircraft had ceased to exist as an integrated structural system well before reaching the surface. From a forensic engineering perspective, the first task was classification. Each recovered component was cataloged by location, orientation, and failure morphology. Investigators prioritized primary load-bearing elements, wing spars, fuselage frames, control surface hinges, because these components preserve the most reliable evidence of stress sequence. Metallurgical analysis revealed a consistent pattern, regions of ductile deformation adjacent to abrupt fracture surfaces. This combination is diagnostic of high strain rate loading, where material transitions from elastic behavior to plastic flow and then to rupture within milliseconds. Wing root fragments were particularly revealing. The fracture faces displayed elongation dimples aligned with principal stress vectors, indicating tensile overload rather than pre-existing corrosion or manufacturing defect. However, microscopic examination also identified fatigue striations beneath the final rupture layer. These striations, invisible without magnification, confirmed that microcracks had been present prior to the engagement. They had not caused failure on their own, but they had reduced the critical stress threshold required for catastrophic propagation. In effect, the missile detonation did not initiate damage so much as activate dormant weaknesses embedded through years of operational fatigue cycles. Attention then shifted to the radar-absorbent material itself. Samples of RAM-coated panels were recovered in varying states of degradation. Laboratory testing focused on adhesion integrity, dielectric consistency, and thermal aging characteristics. Investigators found localized delamination zones where bonding strength had fallen below specification. These zones corresponded closely with areas exposed to maximum aerodynamic heating and vibration during routine flight. While this degradation had negligible impact on structural strength under normal loads, it altered the mechanical response of the skin during blast exposure. Without the damping effect of intact coatings, vibrational energy transmitted directly into the aluminum substrate, amplifying stress concentrations at fastener interfaces. The missile's influence was reconstructed through fragment analysis and blast modeling. Shrapnel penetration patterns were sparse, confirming that proximity detonation, not direct impact, was the primary damage mechanism. High explosive residue analysis matched the warhead composition associated with the S-125 NEVA. The distribution of blast damage suggested an engagement geometry offset from the aircraft's longitudinal axis, consistent with asymmetric impulse loading. This asymmetry explained the immediate rolling moment observed in reconstructed flight dynamics. Investigators simulated the blast interaction using finite element models calibrated with recovered material properties. These simulations demonstrated that even without fragment penetration, the overpressure alone was sufficient to exceed yield stress in multiple skin panels simultaneously. More importantly, they showed how the aircraft's faceted geometry intensified local loading. Flat surfaces oriented normal to the shock front experienced impulse amplification relative to curved geometries. This was not a design flaw in isolation. It was a predictable consequence of prioritizing radar scattering over blast tolerance. The flight control system became a focal point of analysis, not because it failed electronically, but because it functioned precisely as programmed. Data recovered from onboard memory units indicated that control laws responded aggressively to sense deviations. Actuator commands reached maximum deflection rates within milliseconds. However, structural damage altered the effective stiffness of control surfaces, invalidating the assumptions embedded in the control algorithms. In engineering terms, the system entered a regime of model mismatch. Control actions based on an intact airframe accelerated failure in a compromised one. This finding underscored a critical limitation of fly-by-wire architectures when structural integrity is no longer guaranteed. Human factors analysis played a minimal role in the conclusions, not because the pilot's actions were irrelevant, but because the event unfolded faster than meaningful intervention could occur. Ejection timing was consistent with survivability thresholds derived from structural breakup models. There was no evidence of delayed decision-making or procedural deviation. The aircraft transitioned from nominal flight to unrecoverable disintegration in a timeframe measured in seconds, well below the window in which training or experience could alter outcome. The investigative findings challenged several doctrinal assumptions. First, they demonstrated that stealth effectiveness is not binary but conditional, dependent on maintenance state, environmental context, and adversary adaptation. Second, they exposed a systemic vulnerability, the lack of structural redundancy proportional to the aircraft's perceived survivability. The F-117's design philosophy assumed avoidance of engagement as the primary defense. Once that defense failed, the aircraft possessed no secondary layer of resilience comparable to conventional combat aircraft designed to absorb damage and remain controllable. Material scientists involved in the investigation emphasized that none of the failures observed were anomalous. Aluminum alloys behaved as expected under high strain rate loading. Adhesives failed where shear stresses exceeded bond strength. Fatigue cracks propagated along known paths. The catastrophe was not the result of unknown physics, but of known phenomena intersecting simultaneously. The aircraft was operating exactly at the edge of its design envelope, not in terms of performance, but in terms of survivability assumptions. The political sensitivity of the program limited public disclosure, but internally, the conclusions were unambiguous. The loss of the aircraft did not indicate that stealth was ineffective. It demonstrated that stealth alone could not be treated as an absolute shield. Survivability had been reduced to a single pillar. When that pillar cracked, the structure collapsed without resistance. Investigators also noted the operational context. Repeated use of identical flight routes had reduced the randomness upon which stealth doctrine implicitly relied. This predictability transformed probabilistic detection into a cumulative certainty. Over time, even weak signals became actionable through correlation and persistence. The forensic record made clear that the engagement was not a technological upset, but a methodological one. The adversary did not outpace stealth, it waited for it to become routine. In the final synthesis, the forensic narrative converged on a systemic explanation. The aircraft was not defeated by an old missile in isolation. It was defeated by the convergence of material aging, fatigue accumulation, geometric compromise, environmental variability, and operational predictability. Each factor alone was manageable. Together, they eliminated margin. The wreckage, laid out in controlled facilities and analyzed piece by piece, told a consistent story. There was no evidence of sabotage, no manufacturing defect, no maintenance lapse sufficient to explain the loss independently. The failure resided at the intersection of design philosophy and real-world complexity. The aircraft had been engineered for a specific threat environment. That environment had evolved, and the design had not. This forensic phase closed not with blame, but with recognition. The aircraft performed as designed. The missile functioned as intended. The failure occurred at a higher level, where assumptions about invisibility replaced considerations of damage tolerance, and where statistical safety margins were mistaken for guarantees. The consequences of the shootdown did not manifest immediately in public doctrine, but within engineering circles the impact was profound. The event forced a reassessment of how survivability was conceptualized in the stealth era. The loss of a low-observable aircraft to a legacy air defense system did not invalidate stealth as a concept. It exposed the danger of treating stealth as a substitute for resilience rather than a complement to it. From that moment forward, invisibility could no longer be regarded as a terminal advantage. It became a variable, powerful, but finite. One of the first systemic shifts occurred in materials engineering. Designers acknowledged that radar-absorbent coatings could not remain passive, sacrificial layers. Subsequent platforms incorporated composite skins where electromagnetic attenuation and structural load-bearing were integrated rather than separated. This reduced reliance on thin metallic substrates whose failure characteristics under blast and fragment loading were well understood and poorly forgiving. The lesson was explicit. Material failure modes must be considered not only under aerodynamic loading, but under hostile impulse environments. Structural redundancy, long deprioritized in stealth-first designs, returned as a central requirement. New aircraft architectures distributed load paths more diffusely, ensuring that localized damage would not precipitate immediate global failure. Designers accepted modest increases in radar cross-section in exchange for improved damage tolerance. This was not a retreat from stealth, but an evolution toward balance. Survivability was reframed as a layered system, low observability, electronic countermeasures, and structural robustness operating together rather than in isolation. Flight control philosophy also changed. The incident demonstrated that fly-by-wire systems optimized for unstable but intact airframes could become liabilities once structural assumptions were violated. In response, control laws grew more adaptive, incorporating failure detection logic capable of reconfiguring control strategies when sensor data suggested loss of stiffness or continuity. The goal was not to save an aircraft already beyond recovery, but to delay divergence long enough to preserve pilot survivability and, in some cases, limited controllability. Operational doctrine underwent quieter but equally significant revision. Predictability was reclassified from efficiency to exposure. Mission planners reduced route reuse, varied altitudes and timelines, and emphasized stochastic unpredictability as a defensive measure. Stealth platforms were no longer treated as immune corridors through hostile airspace, but as assets whose advantage diminished with repetition. This shift acknowledged an uncomfortable truth. Adversaries do not need to defeat stealth technologically if they can erode it statistically. Air defense analysis absorbed parallel lessons. The engagement validated the continued relevance of low-frequency surveillance systems when integrated with patient, disciplined tactics. While such systems could not provide precise targeting data, they could create situational awareness sufficient to cue other sensors or enable opportunistic engagement. The broader implication was that technological obsolescence is contextual, not absolute. Systems dismissed as outdated can regain relevance when matched against adversaries optimized for different threat spectra. Stealth aircraft that followed incorporated these insights explicitly. Platforms such as the B-2 Spirit and later the F-22 Raptor integrated composite structures where skin and structure were inseparable. Damage tolerance testing expanded to include blast and fragment scenarios previously considered improbable. The emphasis shifted from avoiding detection entirely to surviving partial detection long enough to exit contested airspace. This reframing acknowledged that perfect invisibility was neither achievable nor necessary. Maintenance philosophy evolved as well. Aging effects on stealth materials were treated as survivability variables rather than cosmetic or performance issues. Inspection regimes focused more heavily on detecting subtle delamination and bonding degradation that could influence failure behavior under stress. The goal was not to preserve radar cross-section at all costs, but to maintain predictable mechanical response. In other words, engineers prioritized knowing how an aircraft would fail rather than assuming it would not be tested. At the doctrinal level, the incident eroded the myth of technological finality. Air power strategists recognized that adversaries adapt asymmetrically. Instead of matching stealth with stealth, they exploited cost-effective counters rooted in physics rather than innovation. This realization influenced procurement decisions and threat modeling across multiple domains. Systems were evaluated not only against state-of-the-art opponents, but against disciplined use of legacy capabilities operating outside expected paradigms. Philosophically, the shootdown marked a boundary between eras. The early stealth age was defined by secrecy, novelty, and overwhelming advantage. Its aircraft were conceived as answers to known problems, optimized against specific detection methods. The post-incident era accepted uncertainty as a design constraint. Engineers began designing for the unknown, acknowledging that future threats would not resemble past ones, and that survivability margins must absorb surprise as well as force. The event also reshaped the conversation around progress itself. Technological advancement had been framed as a linear trajectory toward dominance. The loss of the aircraft demonstrated that progress is cyclical, marked by periods of advantage followed by adaptation and counter-adaptation. Each leap forward carries with it new vulnerabilities, often invisible until stress reveals them. This is not a failure of engineering, but its natural consequence. In retrospect, the aircraft did not fall because it was obsolete, nor because its adversary was innovative. It fell because its design assumptions were too narrow for the environment it encountered. The system worked perfectly within the boundaries it understood. It failed precisely at the point where those boundaries ended. That distinction matters because it reframes the event not as a humiliation, but as a data point, expensive, irreversible, and invaluable. The legacy of the shootdown persists in every modern survivability analysis. It serves as a reminder that engineering excellence does not confer immunity from physics, and that dominance achieved through specialization must be protected by humility. The cost of progress is not measured solely in development budgets or program timelines, but in the willingness to accept that no system, however advanced, operates outside the reach of material limits. Stealth remains a cornerstone of modern air power, but it is no longer treated as an invisibility cloak. It is understood as a reduction in probability, not an elimination of risk. That distinction, forged in a night sky over Serbia, continues to shape how aircraft are designed, how missions are planned, and how engineers think about failure. The aircraft's loss did not end an era. It corrected it. In the final analysis, the shootdown stands as a case study in the discipline of engineering realism. It demonstrates that survivability emerges not from any single innovation, but from the integration of materials, structures, systems, and doctrine, all designed with the expectation that assumptions will eventually be tested. When they are, only those systems built to endure surprise remain intact.